Download this code from codegive.com, link in the description below. Professional Data Encryption in Python, a comprehensive tutorial. This tutorial delves into professional data encryption in Python, covering fundamental concepts, common algorithms, best practices, and practical code examples. We'll focus on using the cryptography library, a robust and well-maintained package providing cryptographic primitives in a safe and secure manner. Understanding the basics. Before diving into code, let's establish a foundational understanding. Encryption the process of converting data into an unreadable format, ciphertext, to protect its confidentiality. Only authorized parties with the correct key can decrypt it back to the original plaintext. Cryptography the science of designing and analyzing secure communication techniques, including encryption, hashing, digital signatures, and more. Key a secret value used by encryption and decryption algorithms. The key determines how the data is transformed and is critical for security. Key management, creation, storage, distribution, and rotation, is arguably the most important aspect of secure encryption. Symmetric encryption uses the same key for both encryption and decryption. Faster but requires secure key exchange. Examples: AES, CHA-20. Asymmetric encryption uses a pair of keys, a public key for encryption and a private key for decryption. Slower but eliminates the need to directly share a secret key. Examples: RSA, elliptic curve cryptography, ECC. Hashing a one-way function that transforms data into a fixed size hash value, digest. Used for integrity checks, ensuring data hasn't been tampered with, and password storage. Examples: SHA-256, SHA-3, Blake2B. Digital signatures combines hashing and asymmetric encryption to verify both the authenticity and integrity of a message. Initialization vector, for a random value used with certain encryption modes to ensure that encrypting the same plaintext multiple times produces different ciphertexts. Crucial for semantic security. Authenticated encryption combines encryption with message authentication, ensuring both confidentiality and integrity. Examples: AES-GCM, CHA-20 Poly 1305. Salt a random value added to a password before hashing to prevent rainbow table attacks. 2. Why cryptography library? The cryptography library is preferred over other options, like pcrypto, which is outdated and no longer actively maintained, because security focus designed with security as the top priority. High-level APIs provides user-friendly APIs for common cryptographic operations. Low-level primitives offers access to lower-level cryptographic primitives for advanced use cases. Actively maintained regularly updated with security patches and new features. Well-documented comprehensive documentation makes it easier to learn and use. Strong community support A large and active community provides support and helps identify vulnerabilities. 3. Installation. Install the cryptography library using pip. 4. Symmetric encryption with AES-GCM. AES, Advanced Encryption Standard, is a widely used symmetric encryption algorithm. GCM, Galois/counter mode, is an authenticated encryption mode that provides both confidentiality and integrity. Explanation *. 1 Key generation *. Generate _fernet _key, *, the simplest approach. Generates a random fernet key, which is already encoded for use with fernet. Good for quick prototyping or when you don't need password-based encryption. Derive _key _PBKDF2, asterisk uses PBKDF2, password-based key derivation function 2. This is the recommended way to generate a key from a password. PBKDF2 applies a salt and multiple iterations of a hashing algorithm to make it much harder for attackers to crack the password, even if they get a copy of the encrypted data. Derive _key _HKDF, asterisk uses HKDF, HMAC-based key derivation function. HKDF is more flexible than PBKDF2. It allows deriving a key from any input keying material, IKM. This is useful when your key comes from a source other than a password, example a Diffie-Hellman key exchange. The info parameter can be used to provide context-specific data to further diversify the derived key. To encrypt _AES _GCM, data, key, asterisk. Takes the data, as bytes, and the key as input. Creates a fernet object using the provided key, after encoding the key for fernet. Fernet uses AES GCM under the hood. Calls f.encrypt, data, to encrypt the data. Fernet automatically handles the for generation and encryption. Returns the ciphertext, as bytes. 3 decrypt _AES _GCM, ciphertext, key, asterisk. Takes the ciphertext, as bytes, and the key as input. Creates a fernet object using the key, after encoding the key for fernet. Calls f.decrypt, ciphertext, to decrypt the data. Includes a try, except invalid tag block. Invalid tag is raised if the GCM authentication tag is invalid, indicating that the ciphertext has been tampered with or the wrong key was used. This is a crucial security feature. Returns the decrypted plaintext, as bytes, if successful, or none if decryption fails. For padding, demonstration with pad _data and unpad _data. AES is a block cipher, meaning it operates on fixed size blocks of data, 16 bytes for AES. If your data is not a multiple of the block size, you need to pad it. The code shows how to use PKCS7 padding. PKCS7 adds bytes to the end of the data so that its length becomes a multiple of the block size. The value of each added byte is equal to the number of bytes added. Important asterisk fernet handles padding automatically. The pad _data and unpad _data functions are only necessary if you're working with AES directly, example using cryptography.hosmet.primitives.ciphers.algorithms.aes and cryptography.hosmet.primitives.ciphers.modes.cbc. 5 Example usage, main. Demonstrates the complete encryption and decryption process. Includes an assert to verify that the decrypted plaintext matches the original plaintext. Shows how to handle invalid tag exceptions. Key considerations and best practices asterisk. Asterisk key management is critical asterisk. Asterisk never hard code keys in your source code. This is a major security vulnerability. Asterisk store keys securely. Use a dedicated key management system, example HashiCorp Vault, AWS KMS, Azure Key Vault, or encrypt your keys with a master key. Asterisk rotate keys regularly. Change your encryption keys periodically to limit the damage if a key is compromised. The frequency of rotation depends on the sensitivity of the data and your organization's security policies. Asterisk avoid storing keys in the same location as the data. This makes it easier for an attacker to compromise both. Asterisk protect the salt and store the salt securely alongside the ciphertext. IVs can often be stored with the ciphertext without significant risk, but always consider the specific requirements of the mode you are using. Asterisk use authenticated encryption. Asterisk always use an authenticated encryption mode like GCM or SHA-20 Poly 1305. This protects against both confidentiality and integrity attacks. If you use a non-authenticated mode, like CBC, you must add a separate message authentication code, MAC, to prevent tampering. Asterisk use strong passwords. Asterisk if you're using password-based encryption, enforce strong password policies, minimum length, complexity, etc. Asterisk salt your passwords. Asterisk always use a unique salt for each password to prevent rainbow table attacks. Asterisk choose a high iteration count for PBKDF2. Asterisk a higher iteration count makes it more computationally expensive for attackers to crack passwords. 100,000 or more is a good starting point. Measure the performance impact and adjust accordingly. Asterisk use a cryptographically secure random number generator. Asterisk os.urandom is a suitable choice for generating salts and IVs. Asterisk handle exceptions. Asterisk properly handle exceptions, example invalid tag, value error, to prevent unexpected behavior and potential security vulnerabilities. Asterisk be aware of side-channel attacks. Asterisk side-channel attacks exploit information leaked from the physical implementation of cryptographic algorithms, example timing, power consumption. The cryptography library is generally resistant to many common side-channel attacks, but be aware of the potential risks. Consult a security expert if you're concerned about side-channel attacks. Asterisk regularly update your cryptography library. Asterisk keep your cryptography library updated to benefit from security patches and new features. Asterisk follow the principle of least privilege. Asterisk grant users and applications only the necessary permissions to access cryptographic keys and data. Asterisk perform security audits. Asterisk regularly audit your code and infrastructure to identify and address potential security vulnerabilities. Asterisk don't roll your own crypto. Asterisk unless you are an expert in cryptography, avoid implementing your own cryptographic algorithms. Use well-established and vetted libraries like cryptography. Asymmetric encryption with RSA. RSA is a widely used asymmetric encryption algorithm. It uses a pair of keys, a public key for encryption and a private key for decryption. Explanation asterisk. 1 key generation asterisk. Generate _RSA _key _pair. Generates both a private and a public key using RSA.generate _private key. A key size of 2048 bits is the minimum recommended for RSA security. The public exponent is a commonly used value. 2 Encryption and decryption asterisk. Encrypt _RSA, encrypts data using the recipient's public key. Only the holder of the corresponding private key can decrypt it. Decrypt _RSA, decrypts the ciphertext using the private key. Padding *RSA requires padding. This example uses OAEP, optimal asymmetric encryption padding, which is recommended for its security properties. OAEP helps prevent certain types of attacks against RSA. 3 digital signatures asterisk. Sign _data _RSA, creates a digital signature of the data using the sender's private key. Verify _signature _RSA, verifies the signature using the sender's public key. If the signature is valid, it proves that the data was indeed signed by the holder of the private key and that the data hasn't been tampered with. Padding * digital signatures with RSA use PSS, probabilistic signature scheme, padding, which is a more secure alternative to older padding schemes like PKCS 1v1.5. 4 Key serialization *. Serialize _private key, converts the private key into PEM, privacy enhanced mail, format. PEM is a common format for storing cryptographic keys. Asterisk important asterisk the example encrypts the private key with a password before serialization. This is highly recommended. Never store a private key in plaintext. Serialize _public_ key, converts the public key into PEM format. Public keys can generally be stored without encryption. Load _private_ key, loads a private key from PEM format. If the private key is encrypted, you'll need to provide the password. Load _public_ key, loads a public key from PEM format. RSA best practices asterisk. Asterisk use OAEP padding for encryption and PSS padding for digital signatures. These paddings provide better security than older alternatives. Asterisk use a key size of at least 2048 bits, preferably 3072 or 4096 bits for increased security. Asterisk always encrypt the private key with a strong password before storing it. Asterisk protect the private key diligently. The security of your entire system depends on keeping the private key secret. Asterisk use RSA for key exchange or digital signatures, but avoid using it for encrypting large amounts of data. RSA is slower than symmetric encryption algorithms. For encrypting large amounts of data, use symmetric encryption, like AES, and use RSA to encrypt the symmetric key. Asterisk validate the key size asterisk before using the key, especially if it's loaded from an external source. Validate that it meets your security requirements. Asterisk consider using elliptic curve cryptography, ECC, for better performance and security at smaller key sizes. ECC is becoming increasingly popular as a replacement for RSA. 6. Hashing. Hashing is a one-way function that produces a fixed size output, a hash or digest, from an input of any size. Hashing is used for integrity checks, password storage, and other security-related tasks. Explanation asterisk. 1 hash _ data, asterisk. Creates a hash object using the specified hashing algorithm. Updates the hasher with the data to be hashed. Finalizes the hashing process and returns the digest. 2 verify _hash, asterisk. Hashes the data using the same algorithm that was used to generate the expected digest. Compares the calculated digest to the expected digest. Returns true if they match, false otherwise. 3 hash _ password, asterisk. Generates a random salt. Concatenates the salt and the password. Hashes the concatenated value using SHA-256, or another strong hashing algorithm. Returns the hashed password and the salt. The salt must be stored along with the hashed password. Hashing best practices asterisk. Asterisk use strong hashing algorithms. SHA-256, SHA-3, and Blake2B are good choices. MD5 and SHA-1 are considered insecure and should be avoided. Asterisk salt passwords always use a unique salt for each password. The salt prevents rainbow table attacks. Asterisk do not store passwords in plaintext. Asterisk use a key derivation function, KDF, like PBKDF2, SCRYPT, or Argon2 for password hashing. These KDFs are specifically designed for password hashing and provide better security than simple hashing. Asterisk verify hashes carefully. Asterisk use a constant time comparison function to prevent timing attacks when comparing hashes. The direct == comparison in Python should be constant time for bytes objects, but it's good to be aware of this potential vulnerability. Asterisk regularly rehash passwords. Asterisk if a stronger hashing algorithm becomes available, consider rehashing existing passwords using the new algorithm. 7. Further topics. Asterisk elliptic curve cryptography, ECC. ECC offers similar security to RSA but with smaller key sizes, resulting in better performance. Explore the cryptography.hosmet.primitives.asymmetric.ec module. * Key exchange protocols. * Implement key exchange protocols like Diffie-Hellman or elliptic curve Diffie-Hellman, ECDH, to establish a shared secret key over an insecure channel. * Hardware security modules, HSMs for highly sensitive data.